Hello there, welcome. And today's videos, I'm going to show you on how to use Bouncy Castle library and use some PQC algorithm in your Android Kotlin project. In this case, we are going to use NTRU algorithm plus AES. Okay, for those you who are not familiar with what is PQC, so PQC is basically a post-quantum cryptography or some quantum proof, quantum safe, since the threat of the quantum computer is to fast, fastly crack traditional encryption. So actually, PQC is a project of NIST. They are standardization PQC right now. You can read about it more in this Wikipedia. And regarding the library Bouncy Castle, why I choose this because the first one my boss is recommending me this one, and it is actually a good library which has some implementation in several major languages like Java, C Sharp, and others. It is open source as well and supports so many algorithm, not just for encryption but digital signature or message digest and so on. Right, and regarding the Bouncy Castle, here is some algorithm that they support. There's also information about the package and standard, certification, algorithm and types, symmetric algorithm, AES, which we're going to use, and the message digest, post-quantum algorithm support, and the key encapsulation algorithm or KEEMS. We're using NTRU here, which is now in the round 3 candidate of the NIST PQC competition. It is still going on. The competition is now entering round 4, and the Crystal Kyber is already in the final and fourth standardization. Let's talk about our scenario here. So this is what we are gonna implement today. It's just like TLS handshake protocol. So Alice and Bob is wanting to securely message each other. So the first one is they both gonna generate a key pair. This is called key pair, which is a pair of public key and private key. And we're gonna use the NTRU to generate this one. This is what we call asymmetric encryption. That is an encryption that needs two keys to encrypt and decrypt. And each others will have their respective public key. So here Alice has Bob's public key and Bob has Alice's public key. And we are gonna create a session key. So Alice will have generate whoever init the first conversation will generate AES128 in this case, just for the sake of demo. And the session key will be encrypted using the Bob's public key, and so Alice can safely transfer it to the Bob, and then Bob will receive the encrypted session key and decrypt it using his own private key, and so on, both having the same session key and can message it securely by encrypting each message using the session key. So this one is asymmetric, this one is symmetric. Why we use both? Because both have their own advantage and weakness. The asymmetric keys obviously gonna have larger size and larger computation. If you want a fast and moving, algorithm, you will definitely need to use symmetric encryption. So we are kind of implementing hybrid what TLS does here. And this is the Bouncy Castle for Java. If you want to read about the API, it is here. I will put the link in the description below. And for the library in the Maven repository, we will use this one, or the Bouncy Castle. For now, as I'm making this video, it is in the version of 1.78. It will definitely get updated over time. Alright, let's move in here. I have a basic Android project using the latest Gradle DSL for Kotlin. You know, it's using Toml as the version catalog, and it is, you know, you can follow this without even having Android project, or just normal Kotlin project using Gradle is fine. But I just want to demo it in the Android. So we'll install the library first. I'm gonna name it Bouncy Castle. I hope my video doesn't get too long. It's version 1.78.1, and we're going to name it Bouncy Castle Provider. The provider is good to go. We don't need any other package from the Bouncy Castle artifact. Bouncy Castle, and the name is PC Providers. Let me paste it. This is the name. Alright. Version ref is G cancel. Okay. Now let's add the implementation in our dependency right here. Implementation is going to have eclipse.bouncy. It's not auto completing because we haven't synced the Gradle castle provider. I just sync now. Okay, we are synced, and I have a brand new class here called encryption, and also the unit test encryption test. Since I'm not touching any Android API, so I thought I'd just run it in the unit test. I create a unit test for the encryption. Let's run this, make sure it works. Alright, so we'll mainly focusing in this class. I will use a companion object for it. Okay, the first one is we need to register the provider name. Okay, so we're gonna call security from the Java security, and then add provider and the Bouncy Castle provider. So this for provider is for the symmetric algorithm, and then for the PQC we need to register another one, call it Bouncy Castle PQC provider. And after that we're gonna tackle this use case. We'll generate a boilerplate for what function do we need. So for the first one, we're gonna generate a key pair. I will leave it there, and then the second one, we're gonna generate session key. So the key pair is asymmetric using NTRU. We're gonna comment this out NTRU, and then this one is AES, which is symmetric. Alright, and after we have the key pair and we have the session key, the next one is to wrap or encrypt the key. So we're gonna have a wrap key function. I'm sure this one is recording, right? Okay, thank you. And then the opposite of it is unwrap the key. After that, then we basically need the encrypt key and decrypt function. That's how we do this. Excuse me for a second. Okay, it's now running. After we generate this Bouncy Castle provider, you can see here, if you control click it, there are several algorithms that is supported in symmetric cipher, such as AES, IDEO, and so on, as well as the Bouncy Castle PQC provider supports some algorithm like NTRU, NTRU prime, and so on. So we're gonna grab that and we're gonna create several constant here. The first one is gonna be provider name. Yeah, it's gonna be BC for the symmetric one. As you can see, provider name is BC. Yeah, I'm hard coding it right now. You can just grab it from the class. Const file the PQC provider name. Maybe BC PQC if you look at it. BC PQC. And we're gonna specify the algorithm name for symmetric algo. We're gonna use the AES and then private cons of we can specify the symmetric key size, which is 128 bit or 16 bytes of the secret key, and then the asymmetric algo, which is going to be NTRU. And to generate key pair, since we are already adding our provider, we can just use the built-in key generator function inside the Java crypto library. So we're gonna call key pair generator, and then we get instant. What instant do we need? It is the asim algorithm, and then the provider is PQC provider name. Just like that, we get the key pair generator here. And we're gonna initialize the key pair generator, keygen called initialize, and we need parameter specs. So the NTRU it is not a single algorithm. There is a plenty of a variant of NTRU like NTRU, HRS or HPS, which some several parameters, and you can actually read it online or ask AI to explain the difference. For now, I will just call it NTRU parameter spec. We call G parameter spec dot. This couple here, and I'm gonna use the HPS. This one, since I believe this one is the lowest size in byte, so it's useful for my use case. After that, we're gonna pass in the parameter spec here. So we are initializing the keygen using this NTRU variant of algorithm. Now we need to return the key pair using the keygen.generate key pair. And the return type, obviously a key pair. If you take a look at the key pair, it is having two private key and public key. Two key, okay. We already generate the key pair. Now we need to generate a session key. This one is easy as well. Just create a key generator. This one is key pair generator and this one is key generator. Remember that. And we get instant. This one is symmetric algorithm, and then the provider name is going to be the provider name. So we're going to get instant of AES from the BC library. BC stands for Bouncy Castle, obviously. Now we need to keygen.init, and the key size is going to be the same the key size. I'm going to return keygen.generate key. and the return type is going to be secret key. I'm having a problem here. What was it called? It is integer sim keys. Oh, okay, sorry, this mistype here. It is should be integer. Thank you. And now it is the wrap key. So we need to wrap the session key or the AES key using the NTRU. How do we do that? Well, remember in our use case here that, for example, in Alice's point of view, she need Bob's private key. So it's gonna be the target public key. So the first parameter obviously is gonna be the key. It's gonna be a secret key, and then the target public key. It's gonna be public key. And the return is gonna be byte array. You know, the return of wrapping a key is gonna be byte array. Excuse me, and the file we're gonna use cipher this time. So cipher get instance of the symmetric logo, and then the PQC over there. So we get a cipher, and then we need to initialize the cipher. So cipher init, what do we init? So cipher has in some mode, that is wrap mode, unwrap mode, public key, private key, decrypt mode, and encrypt mode. Since NTRU is only a key encapsulation algorithm or key AIM, he's not support any mode other than wrap and unwrap mode. So decrypt mode, encrypt mode doesn't work if you are using the NTRU. That's specific for wrap and unwrap key. So we're gonna wrap mode, and then we need the public key. So we need the target public key. After that, then we can return the result with cipher.wrap. What kind of thing we need to wrap? It is the key. And that's how you wrap a key. And to unwrap it, you're gonna do vice versa. You're gonna call this one is wrap key, which is gonna be a byte array, and then my private key. You know, this scenario right here. And the return is gonna be the secret key. So we initialize the cipher again. So cipher is gonna be cipher get instance of asymmetric algorithm of NTRU and the PQC provider. We're gonna need to init, sorry about that, and this mode is gonna be cipher.unwrap mode. We use my private key. I'm sorry, I'm not specifying the type of private key. This one should be a private key. And the return is gonna be cipher.unwrap, and this one takes three algorithm: the key, the wrapped key, the wrapped key algorithm, and the secret key. So the wrapped key there, the algorithm is gonna be symmetric algorithm of the key, which is AES, and the secret key we can use the cipher.secret key since we are already registering the asymmetric algorithm here. Okay, this one should be a secret key. We can just typecast this one as secret key, and we're done. Actually, for the encrypt, this one is easy one. So we're gonna have session key. Yeah, this one is unencrypted, and it is a byte array, and we're gonna need obviously the message to the string. The return is going to be a byte array again, and this one is using the engine. So we're gonna define an engine. This one we're gonna use this directly from the Bouncy castle. The like engine here, and engine that in it. What we need is for encryption. It is true. This one is for encryption, and then the cipher parameter is gonna be key parameter from the session key, just like that. And then we need to store the byte size of the message. So message byte, it's gonna be a message to byte array, and then the block size. Okay, sorry, the block size is going to be engine.block size. There we go. And then the padded length. Okay, the padded length is going to be message byte size divided by block size, and we're gonna times the block size right there. Oh, we forgot to +1 this one. Let's wrap it in bracket here, and we're gonna go define the result. It's gonna be byte array of the padded length. This one is actually, we are calculating the size of the result of our encryption. The actual encryption is here. We padding length. No, it's padded message. We forget to copy the message, so we copy the message first. So padded message gonna be message binds to copy of with the size of padded length. And for the padded length, padded message, indices, and for the step of the block size, we're gonna process that block. So engine process block, the padded message, the offset, and the output. We're gonna use the result byte array, and then the output offset is gonna be the I, and we're gonna return the result. Quite long, I guess, but you can find this online. This one is generally available. The documentation is pretty clear out there. You should be able to copy that from somewhere. So I'm just gonna type in all of this stuff. I'm gonna save your time. So the cipher text is gonna be byte array, and then we're gonna come back with a string of the encrypted message of our engine. I'm gonna copy from this one, and the block size is the engine block size. Okay, the result of our result is gonna be byte array from the ciphertext size, and then for I in ciphertext indices, step of block size, we're gonna process the block again. So engine the process block, the ciphertext, the I, the result, and the I, and return the result. And that's how you actually. What else wrong with this? Alright, this is still by the RAM, so we're gonna use string and assemble this result. We're gonna trim a space here. It should be a lambda and a space. Oh, what went wrong? Okay, it's char. Char is right there. All right, let's test this one. Okay, let me rerun this one in case any error. All right, we test. So we're gonna define a before block, or we shouldn't. Yeah, it's better to, before everything we gonna set up here. Here we're gonna call a private late var. We're gonna name it Alice key pair. KP is just for key pair. You're gonna have key pair, and we're gonna have Bob key pair. Okay, and for each setup, we're gonna generate a key pair and private. Actually, no, we don't need that. So Alice key pair is gonna be encryption dot generate key pair. Bob key pair is gonna be encryption generate key pair. Okay, and we're gonna have several tests here. Then the first one is gonna be testing key pair on a load key pair. So test key pair. Copy this one. The second one is gonna be key generate session key. Test session key. Third, hey, sorry about that. Third one is gonna be test wrapping key. And the last one is gonna be test encrypt. Decrypt. Right. Start from testing the key pair. We actually gonna have a val Alice pub key. Gonna be Alice key pair the public key. Encode it. Val Bob. No, Alice private key. Alice key pair the private. Then encode it. We're gonna do the same for the Bob. Bob public key. And Bob pub key. And Bob private key. Is Bob KP and Bob KP. Right. And we're gonna load this one. So I won't take long. Alice. So we're gonna load the size. This one is byte array. So we're gonna just load the size here. Alice. Alice pub key size bytes pub print Alice private key size. Let's do the same for Bob. So Bob pub key is gonna be Bob pub key and Bob private key size. Okay, let's run this one. Up nothing error. As you can see here, Alice public key is 727 bytes. If you really want to know what is inside, it actually is a byte. Let me just log the Alice public key. It's gonna be Alice public key dot this one. Right. And one more is pub key to hex string. You really want to see this hex string representation. Let me update this one, and if you look this one, no, that's the key. It is so long, so freaking long, right? So we successfully generate the key pair. Now let's go the session key. Let's generate the session key. So val session key. It's gonna be encryption dot generate session key. Very descriptive. Session key is in what bytes? I'm gonna log the size as well as the session key dot hex string representation. It's session key dot size here. Encoded size. Let's test the encryption session. There you go. This is session AES128, which is 16 byte. This is success. Now the actual test is for wrapping. We're gonna create a session key. We're gonna log it. Let's open and let's actually wrap a key. So wrap a key, in this case communication dot wrap key is take the key, which is going to be the session key, and then the target public key. For example, this one is Ali's point of view, so we're going to use Bob, the public key, right? And we're gonna log the result. Let's private key here. It's not encoded. Private key is not encoded. So that's the private key, and we're gonna test unwrap it. So the unwrap will have the same as the session. So unwrapped key is gonna be encryption dot unwrapped key. The wrapped key is wrapped key, and then the private key is the Bob KB private. So this is Bob point of view in receiving Ali's session. I'm gonna print this one as well. Okay, name it rabbit key, and this one is unwrapped key. It is unwrapped key size. This one is encoded size. This one is encoded. And let's assert this one. So it's going to be assert, since it's byte array against byte array, we're going to assert array equal. Uh, why you're not importing? Okay, let's manually import this. I hate this. It is from the JUnit assert. So import push JUnit assert 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 array equals. There we go. I don't know. So assert array equals, and we're gonna do assertion in the session key and then the unprivate key. Is it correct or not? And I'm not. Okay. This one is still a secret key, so we need to take the key which is encoded. Why this doesn't want to? Why this doesn't resolve? Alright, this one is my bad. Okay, let's test the wrapping key. Okay, it's successfully wrapped. So this is the original key. We wrap it, so it's long, around 700 bytes, and then we get the original after we unwrap it. So the wrapping is success. Now let's see the encrypted crypt. We definitely need a message. We call it hello mom, and we're gonna encrypt the message. Encrypted message in the encryption.encrypt. We only need the session key. So we need to create a session. While session key. Encryption generates session key, and then the message. What's wrong? Okay, the encrypt is yeah. Let's just take the encoded and the decrypted message. Encryption decrypt session key dot encoded, and then the encrypted message. Now let's print and let's see the size. We have the original message, which we'll need to know the bytes, and the actual message. There's gonna be message byte array dot size. I'm gonna load the encrypted message size, since it's already a byte, and it takes this to string or to hex string. Let's go to hex string and open this experimental API. Alright, now for the decrypted message. Decrypted. Alright, I'm sorry. This video takes longer than I expected. The byte array size. And let's test it. There you go, it's passing. So we have hello mom encrypted this one, and decrypted is, why does it look so ugly? Is there anything wrong with this? Okay, this is why we need unit tests, obviously. Let's just see what's wrong here. I hope nothing serious. Let me pause this one. Alright, I just realized I got it wrong. So the decrypt one, the engine is not for encryption false, and so we should actually do the assert equal here. Assert equals the encrypted message is gonna be the same as the decrypted message. Let's go. This should do the job, I guess. No, it still failed. Why is it that? Oh, it's message. Sorry. The original message should match the decrypted message. And there you go. It is hello mom and encrypted as this, and back to hello mom. Only 6 byte increase using symmetric IAs. And let's actually run all the tests to see what's going on. There you have it. Thank you for watching. Maybe I will publish this source code and the link will be down below. You feel free to comment and do whatever you want. Thank you very much. See you soon.